Okay, today we're going to look at gases. Gases are interesting to study for high school students because you can very easily, with the math that you already know, understand all the laws pretty much that we know about gases completely. To understand the properties of gases, one thing that we have to be able to understand is the idea of pressure. Pressure is defined as a force applied over an area. So mathematically, we can define pressure this way. It's the ratio of the force that you put on something divided by the area over which you apply that force. Now, if you think about the units that you would have to have in the SI system, we measure force in the Newton, and area, well, we measure area in meters by meters or square meters. So Newton per square meter would be the unit, standard unit of pressure. But a Newton is a fairly large force for gases, and a square meter is a pretty big area, and so we're not going to use that often as our regular unit. Most of our units of pressure are actually going to come from this idea, atmospheric pressure. And the idea behind this is, here's the Earth, you stand on the Earth, and you, like all the other objects on the Earth, are attracted to the center of the Earth by a gravitational pull. And we understand the nature of that gravitational force because we've studied it already. But you're also surrounded by this band of air molecules. It contains trillions and trillions and trillions of nitrogen and oxygen and other particles, molecules. And those particles, every one of them is attracted toward the center of the Earth by gravity, just like you are. And so we have this collection of air particles that's all pulled towards the center of the Earth, and the whole total of those exert a pressure. If you pick any square area of surface on the Earth, it's going to have a certain amount of pressure that's exerted by the force of those air molecules banging on it. It's kind of like a steady, consistent push, but it's made up of many little collisions of air molecules on that square on the center of the Earth. Well, we measure that by the use of a barometer. This is a tool that was invented by a guy named Evangelista Torricelli. And Torricelli was an assistant to Galileo, who was a really famous scientist from long ago. What it does is it uses a mercury column to measure relative air pressure. So the idea is you have this long skinny tube, kind of like this, and this tube has been filled with mercury. Originally it was not in the orientation that it is right now. It was right side up, but the opening here, there's an opening, and that would be facing up, and then it's filled with mercury, and then it's placed into a bowl of mercury. So it's inverted, placed into a bowl of mercury, and then the person takes their finger away from the opening, and then a force balance gets set up because this has a weight, Fg, that's going to be equal to its density, the density of the mercury times the volume of the mercury, times G. So that's mass times G. But there's something pushing up, and what's pushing up is the force due to the atmosphere. And that force gets transferred around so that it also pushes up on the column. And so when the atmospheric force matches the gravitational force, well, we have a column that's just high enough to do that, and we can measure the height of that column from there up to there. And if we measure that, that gives us an idea of, compared with yesterday's measurement or tomorrow's measurement, what's the current atmospheric pressure. Most of the time we measure this using units of millimeters in science, and so we call this the millimeter of mercury. And most of the time, most people live at about where the atmospheric pressure averages out to approximately 760 millimeters of mercury. And that's actually turned into a unit that we'll talk about later. Most people on Earth, almost everybody on Earth, lives in a range of about 730 millimeters of mercury to 760, or approximately 760. Most people are in that band. At the top of Mount Everest, the atmospheric pressure on Everest, I'm going to say, that's equal to about 250 millimeters of mercury. It's much lower, and here's the reason for that. If we think about the atmosphere, I'm going to make an exaggerated drawing of Mount Everest. There's Mount Everest. At sea level, the pressure on a square inch or square meter or whatever is basically the weight of this whole column of atmosphere. But if we look at the column of atmosphere on the top of Mount Everest, well, it's a shorter column, and so it weighs less, and so it exerts less pressure. So anytime you go up in elevation, when you go up a mountain, the pressure drops. Here are some pressure units that arise from the use of the barometer. First of all, there's a unit called an atmosphere. 1 atmosphere is equal to 760 millimeters of mercury, which is the average air pressure at sea level. So since that kind of averages out to that, scientists have defined this, and they call this a unit of pressure. 1 atmosphere is the pressure that exists when 760 millimeters of mercury show on the barometer. So torrs, well, a torr is just a fancy name. It's named after Evangelista Torricelli, actually, for a millimeter of mercury. That's what a torr is. 1 torr equals 1 millimeter of mercury. And so 760 torrs equals 1 atmosphere. Inches of mercury is another unit of pressure. It's related to barometer use. In the United States, meteorologists and some other people use inches of mercury. It's the same thing as torrs, except instead of measuring with a meter stick and getting millimeters of mercury, you're measuring with a yardstick and you get inches of mercury. Here's the relationship. 29.9 inches of mercury is the same thing as 1 atmosphere. The Pascal is the renaming of the standard SI unit of pressure. A Newton of force over a square meter, that's what we call a Pascal. Here's the relationship. 1 atmosphere is equal to 101,325 pascals. So you can see that a pascal is a really small unit of pressure. Sometimes people will use kilopascals, so there of course would be 101.325 kilopascals per atmosphere. Another unit of pressure that's fairly common in laboratories and it's often used in low pressure situations is the bar. A bar is equal to 100,000 pascals. It scales up to pascal a little bit. Here's another relationship that's useful. 1,013.25 millibars, so those would be thousandths of a bar. Well, that's equal to 1 atmosphere. So you could convert if you needed to. And in good old-fashioned U.S. units, what mechanics, and if you check your tire pressure, most likely this is the unit that you use, a very common unit for pressure in the U.S., it's pounds per square inch. And really it represents how much force in pounds for every square inch. And here's the relationship. 14.7 pounds per square inch is the same thing as 1 atmosphere. And in these common units that we're used to, this should give you some idea of just how big the force due to the atmosphere is. Every square inch of your body is being pushed on by 14.7 pounds. That's about the weight of a bowling ball. That adds up to a lot of force. Of course, we don't notice it because we're used to it. There are some relationships that tie together pressure and some other quantities that we already know about. One of these is Boyles Law. Boyles Law says that the volume of a fixed quantity of gas held at a constant temperature varies inversely with the applied pressure. So mathematically, we'd say this. The volume is proportional to, that little symbol there means proportional to, the inverse of pressure. If you were to graph volume versus pressure, like this, you'd find a relationship that looks something like that. As the pressure gets bigger, the volume drops. How we know it's an inverse proportionality is if you plot 1 over pressure versus volume, you get a straight line relationship. Now, this only works if the amount of gas is a fixed quantity and the temperature doesn't change. If the temperature changes, then this relationship isn't probably going to be true anymore. Here's something interesting. If we take this proportionality here and we turn it into an equation, this is what we get. Volume is equal to a constant number times 1 over pressure. That constant number is just going to be the slope of this graph here. The slope of that is K. Well, if I solve for that constant number, here's what I find. Pressure times volume is a constant. So let's say I take a look at this relationship here this graph, and I picked 2 points. Here's point number 1, corresponds to P1, and here's point number 2 that corresponds to P2, and P2 corresponds to V2, and P1 corresponds to V1. Both of these points, the product of their pressure times their volume is equal to the same K because they're on the same line with the same slope. So that tells us that P1 times V1, the product of pressure and volume for one condition, is equal to P2 times V2. So this is a useful relationship. It's called the two-point form of Boyles Law that you can use to solve all kinds of problems. We're given the volume of a balloon, it's 500 milliliters, when it's at sea level, and the pressure is 760 torr. Goes up to the top of a mountain, and of course the pressure is going to drop. What we see happening is the volume goes down too. Assuming that the temperature on the mountain is the same as at sea level, and the balloon hasn't leaked, so we could use Boyles Law to figure out the answer to this question. What is the pressure at the top of the mountain? Well, let's set this up this way. Let's say pressure at sea level times volume at sea level is equal to pressure on the mountain times volume on the mountain. And then what we're trying to find here is volume on the pressure on the mountain. That's what we're trying to find. So we'll solve for that. So pressure on the mountain is equal to pressure at sea level times volume at sea level divided by volume on the mountain. And then we'll plug in our data that's given to us. Well, the pressure at sea level was 760 torrs. The volume at sea level was 500 milliliters, and the volume on the mountain was 750 milliliters. The volume has gotten larger. Milliliters cancel, and so the pressure on the mountain is going to be given to us in torrs, and when we do our calculation we find out that it's 507 torrs. That's a drop in pressure, and that's what we'd expect when we go up a mountain. Here's an illustration of that from a vacation that I took once. These are my kids and I sitting at a tea house that's very near the top of a high mountain in the Canadian Rockies. And take a look at this water bottle. There's a little water in there, but I drank all this water and sealed it up so that there was some air in there, which is a gas. And that night we took off on a drive, and we headed west, and we went to the coast with this water bottle sealed up in my backpack. Well, the next day we were in Vancouver. You can see here, this is my son standing there with the same water bottle in front of the North Vancouver Hotel. Vancouver is at sea level. It's right on the ocean, on the coast. And here's a close-up of the bottle. Look at what's happened to the bottle. The bottle has actually collapsed. Its volume has gone down because the pressure went up as we came down from a high mountaintop to